Okay, so I am going to cover about energy in chemistry. What we've been doing up to this point is it's been showing you chemical reactions, which is with matter. But we're going to see that energy is also important in chemistry, and sometimes more important. Or okay, so far, when we look at chemical reactions, we just see the substances that are being changed. For instance, when we have propane plus oxygen yields carbon dioxide and water. And then we came up with the balance equation. And this particular reaction is quite useful to a lot of people. It's actually the reaction we use. A lot of people use to heat their house and to grill things up. Okay, but when we do this chemical reaction, we really don't care about these guys all too much, especially these products. We don't care about the carbon dioxide and water. We really care about what's happening, what else is happening, which is the heat that is given off in this reaction. And so what we want to do is focus on heat of reactions here. So all chemical reactions either release heat or absorb heat. And in this case of the combustion of propane, heat is released. So we really should add it to the chemical equation. So we have propane plus oxygen yields carbon dioxide and water and heat. Okay, so heat is actually part of the chemical equation. Now, for the most part, we leave it off, and that's because we just often just concern ourselves with these substances. But honestly, we should keep it on here. And then here's the symbolic equation. But heat, like I said, is a very important part of chemical reactions. Another chemical reaction that's important to us all is the combustion of gasoline. Gasoline is essentially alkane molecules, mostly octane. So basically, the chemical reaction is octane plus oxygen yields carbon dioxide and water and heat. Okay, and then you can write it like this. And what happens is these two guys are formed, and the heat is formed. And what the heat does is it causes these guys to expand into pistons, and the piston moves in and out because of that. Okay, so it's kind of important to have these products, but really the main driver of this reaction, why our cars move, is the heat that's produced. Now, for a really long time, we really didn't care about these two things, carbon dioxide and water, okay? But these days, we are becoming more aware that the carbon dioxide that is given off during combustion reactions is really important because it releases carbon dioxide into the air, which has an effect on global warming and climate change. Okay, here's another chemical reaction that you need. Everybody needs this one. So you have glucose, and glucose is the primary food we eat. Okay, it's in all food. You may not even know it. Okay, it's a sugar. Okay, and it's not it's not the kind of sugar that you go grab at the store, but it's kind of like it. But it's found in vegetables and meats and everything. And when you eat it, it goes into your cells. And then when you breathe oxygen, the oxygen combines with the glucose. It combusts and forms carbon dioxide and water. So you breathe in oxygen, you breathe out carbon dioxide, and water is also made. Okay, but the key thing is heat. And the heat, what it does is it causes our muscles to move and our cells to work. This chemical reaction here, okay, when you take biology or anatomy and physiology, you will learn that it's called cellular respiration. But it's nothing more than a combustion reaction. You take a carbon substance, add the oxygen, forms carbon dioxide and water, and heat. All combustion reactions give off heat. Okay, now there are some other reactions that instead of releasing heat, absorb it. For instance, if you grab some ice, it begins to melt. Okay, what is happening is the heat that the ice that's melting is taking the heat from your body, put it into the ice, and causing it to melt. So what is happening is heat is going into the ice, and you're making water. Okay, this reaction absorbs heat instead of releasing it. Most chemical reactions release heat, but some will absorb heat. Okay, heat is a form of energy, and I will be covering more about energy in a few minutes. So technically, when we write heat in an equation, we could replace it with the word energy. And so we get this. Okay, so you can kind of relate to this now. You have glucose, all right? You breathe in oxygen, it gives off carbon dioxide and water, and it gives you energy, okay? All right, this is your energy to do your life. Now, another example of a reaction that absorbs energy is photosynthesis, which plants do. They do the opposite of cellular respiration. They take the carbon dioxide that we breathe, the water that we give off, and they combine it with solar energy, and they make glucose and oxygen, which, guess what? We can take that, eat the glucose, breathe the oxygen, make carbon dioxide and water, and guess what? It can go back into the plants. It's a beautiful cycle. This is the reverse of cellular respiration. Photosynthesis requires energy, while cellular respiration gives off energy. When a chemical reaction releases heat, like in combustion, we call it exothermic. Exo means out, thermal means heat, so heat out. When a chemical reaction absorbs heat, we say it is endothermic, which means in. Endo means in, heat. Thermal means heat, so heat into the reaction. So cellular respiration is exothermic, photosynthesis is endothermic. All right, so let's talk about energy. We this word just flops around in our daily lives, and we sense we know what it is. For instance, you feel tired and you say you don't have much energy, or you say you are amped up and you have a lot of energy. So why do you need energy? Why do we need energy? Basically, to do anything, you need energy. When you do something, it's what we call work. So the definition of energy is it's what we need to do things or to do work. To do anything, you need energy. And that's it. So energy is directly converted into doing work. So if you have energy in you, it will be used to do work. Okay, energy doesn't technically just get lost, so you don't lose energy. What it does is it moves from one thing to another. So once you do some work, you go, I'm tired. Okay, you lost energy, but not really. That energy has not been lost. It's moved to somewhere else. But it's still the same amount of energy. Okay, it turns out the amount of energy in the universe is always the same. It just moves around in different forms. And one of the forms is work. This is a basic law, the law of conservation of energy, which basically says the energy is not created or destroyed, but only can be transferred. So energy moves from one thing to another. Notice it's like the law of conservation of matter, or mass. Matter is not created or destroyed as well, but it can be transformed into other types of matter. So both of these say that the amount of energy in the universe and the amount of matter are constant. Okay, Now, a little bit more about energy, and there's not all just one type of energy. Energy can show up in different types, such as heat, light, chemical, gravitational, all kinds of different ways. But it really only has two forms, kinetic and potential. And we want to go over these. Kinetic energy, it's when things move, they will have energy. For instance, when a moving bowling ball hits bowling pins, it has energy. The moving bowling ball has energy. And when it hits the pins, it transfers that moving energy and to knock down the pins. We know that kinetic energy is taking place. In fact, normally the energies that we see taking place, and the cars moving and wind blowing and our legs moving, it's all kinetic energy. Now, heat is a form of kinetic energy, or a type. Heat is made when molecules move. So when molecules move around, that movement causes heat. Okay, so when you feel heat, you're feeling the consequence of molecules moving around. Light is also a kind of kinetic energy, but instead of molecules moving around or atoms, it's the actual electrons on the atoms that are moving. Potential energy is energy that's stored. It doesn't do work now, but it can come out to do work. Now, it's really hard to tell if something has potential energy, because if you look at something and go, I can't tell if it has energy or not. But, I mean, if there's a piece of wood sitting on the table and you go, hey, I don't know if that has potential or not because it's sitting there, but it may have potential energy stored in it. For instance, if you take a book and you lift it up and you hold it up in one spot, okay, maybe 2 feet off the ground, okay, and you don't let it fall, you know that once you let go of that book, it will be pulled down to the ground and it will start to move. Okay, so you know it has the ability to move. So it has kinetic energy and it's stored in it right now because it's not moving. But once you let it go, it becomes kinetic energy. So you know the book has kinetic energy, but as soon as you release it, when you're holding it, and therefore it's potential energy. But once you release it, all of a sudden, all that potential energy eventually becomes kinetic energy. Another example of potential energy is in us. Maybe you said, I don't have the energy to do something. Right? No, the reason why you may have said this is because you're tired. Or you just don't have that get up and go. Okay? And the reason why is that you don't have energy stored in your cells that can come out to help you move. Okay, to get turned into kinetic energy. Okay, so what we do is we have stored chemical energy, potential chemical energy stored in different parts of our body that's all ready to be turned into kinetic energy to help us live life. Okay, notice that potential energy can be turned into kinetic energy, like when I held the book and then dropped it. But the opposite is true as well. You can have kinetic energy turned back into potential energy. For instance, how did the book get up to where you held it? Well, you had to move it up. So the moving up is kinetic energy, and then it's held. Now it has potential energy, and then you drop it. It has kinetic energy. So the kinetic energy, and there's kinetic energy to raise the book. That energy that rose it is actually how much energy it takes to hold it up there. And then when you let it go, it's how much energy is released. Okay? So notice there's a transfer of energy from kinetic to potential, and then from potential to kinetic. Okay. All right, so you can go back and forth between potential and kinetic energy. You can also go from kinetic energy to kinetic energy, but you can't go potential energy to potential energy. Okay, like when you have the bowling ball, and it could smash into the pins and cause the pins to move. That's kinetic energy into kinetic energy. Okay, you can take kinetic energy and turn it into potential energy. Okay, and you can have potential energy turn into kinetic energy. But you can't have potential energy turn directly into potential energy. Okay, the only way you can do that is, first of all, get it moving. Okay, so you'd have to go kinetic energy first and then the potential energy. This won't work. Okay, units of energy. All right, energy has its own units. You're probably familiar with calories. Okay, we talk about when you eat food, you're eating it for the calories to keep you awake or whatever. By the way, if you take a drink like 5 Energy and it says it has no calories, that means it doesn't have energy in it. So it's 5 Energy drink is actually a misnomer. It actually has no energy in it. Okay. It's a lie. Okay, but what it has is it has caffeine, which is not energy either, right? And so there's a lot of little things about that I don't like. But anyways, back to calories. So when you eat food, you eat it for the calories, and the calories get stored in your cells. The calories of the food get stored into your cells, and then when you need energy to do work, that energy is removed from the food you ate to do work. So we use calories as a unit. There are other units as well, such as BTUs and joules. Those are more specific for different kinds of things. We will use calories. It turns out that calories actually have 2 versions. One version is the word calories, which is technically a scientific value. 1 calorie is how much heat is required to raise 1 gram of water by 1 degrees Celsius. So if I want to take 1 gram of water and I want to raise it by 1 degree Celsius, I have to add 1 calorie. Now, the calories we talk about when we talk about food are actually 1,000 scientific calories, or 1 kilo scientific calorie. So if we are told to eat 2,000 calories a day, food calories, that is actually 1,000 times scientific calories. So if you eat 2,000 food calories, that's actually 2 million scientific calories. So when something says it only has 1 calorie, really, it's 1,000 calories. All right. The way that we will talk about scientific calories. So when you hear scientific calories, it will look like this. If you were actually to talk about food calories, you would use a capital C. All right. Okay, energy of chemical reactions. So all chemical reactions have some sort of energy, either are being absorbed or released. So let's go back to the exothermic reaction of the combustion of propane and relate it to kinetic and potential energy and see what is happening. We have to remember that energy is conserved. So here's our chemical reaction. Okay, we're going to replace heat with kinetic energy because it's moving. So when this chemical reaction takes place, molecules start bouncing around, and that gives off heat. Notice that energy is only on the product side. Okay, and I said that energy needs to be conserved. So if we notice it's only on this side, the product side, and it's not on the reactant side. Well, you can't just create energy. So the energy, this energy somehow must have been over here. Well, where is it? I don't see it in the equation. Well, it's hidden inside these guys. Okay. So there's energy stored inside these guys. It's like potential energy. Okay. And, I mean, these guys. And when the reaction takes place, that energy is given off. Okay. And some of it stays in carbon dioxide and water, but some of it is given off as heat. Okay, so one way to think about it is think about a balloon. Okay, so if you have a balloon, all right, here's your balloon. You start out with, okay, and then what you do is it's got a certain amount of air in it. And what you're going to do is you're going to take a pin and you're going to poke it, all right. Now, when you poke it, okay, so getting telephone calls, interrupting me. So you put the pin in, okay, and what happens is the balloon shrinks, okay. All right, it lets out air. But the other thing it does, and the air actually comes out pretty explosive, and it actually will make like a sound, like a psss. Okay, now if the balloon had a lot of air, you would get a bigger if you had a little balloon, it would go so, okay, so one thing you could do, possibly, so what you have here is that this guy has stored energy in it, and this guy has stored energy in it. Okay, so this has stored energy, and this has stored energy. So this guy, you can tell, has more stored energy. You can see it's bigger. Okay, and this has less stored energy. You can see it's smaller. But by how much? Okay, well, one way to do that is to measure this sound. Okay, if it gives out a big sound, you can figure out how much the difference in the size of the balloons are. If it gives off a little sound, it'll be a tiny change in the size of the balloons. Okay, so that's what we're going to do with chemistry. What we're going to do is, what we want to do is we want to know how much energy is stored in each of our substances. This is the reactant. We call this the product. Now, we can't measure it directly. We can't weigh the amount of energy in here, and we can't measure the weight energy in here. But what we could do is measure how much energy is given off, or the change in energy. I mean, the energy that's given off. And this energy that's given off directly relates to the size of the balloons, the difference in the size. So if I have a relationship, I know this amount of sound is this difference in size, I can tell you the difference in size is in the balloon. So that's what we're going to do in chemistry. What we want to do is find how much energy is in one side and how much energy is in the other side. And the way to do that is that we can't measure each guy's individual energy, but what we can do is measure the energy that's given off when we do the chemical reaction. And when you do that, this amount of energy that gives off is going to be the amount of energy that's different between the two. So the change in energy is going to be the same, have the same amount as the difference in energy. Okay, so in this particular case, we have an initial balloon, our big guy, and then we pop it, and then we get a final size of balloon. Right. And that energy is given off as psst, and whatever the energy given off is the difference between these two, the energy inside these two. So the internal energy. So we can say is energy's been given off, so we can say that the energy is negative, and we don't have to worry that for this class here. Okay, exothermic reactions where products have less internal chemical energy than the reactants. Some chemical heat energy is converted into kinetic energy. The reaction releases heat energy into the surroundings. We're going to show that. And everything gets warmer, and you'll see that. Okay, so our example is you take our reactants, turn it into our products, and it gives off heat. This heats our surroundings. All right, so let's take a look at, in this case, combustion of methane. So you take methane and oxygen, and we're going to kind of say that this balloon represents how much energy are in these two guys. Then you do the chemical reaction, you make carbon dioxide and water, and again the balloon represents how much energy is inside these two products. Okay, we find out that the reaction gives off heat. That means that the product have less energy than the reactant by this amount of heat. Okay, so the difference in these two, the reactant and the product's internal energy, is how much heat is given off. Okay, and again, this is, you can write it out, and this is the propane, but same idea. So when you combust propane, it gives off heat, and it makes carbon dioxide and water. This would be have more heat in it than this guy here. And what we're going to want to do is figure this value out. Okay, endothermic reactions, which is the opposite. These reactions absorb heat, we said. Okay, the energy has to go into the chemical reactions. The surroundings loses heat, or things get cooler, and the temperature decreases. All right. So in this case, the heat energy goes into the reactant side. For instance, we have photosynthesis. Okay, here's the reactants. You add heat to the reactant side, or energy, I mean, and you produce glucose and oxygen. Okay, so these reactions absorb heat, and in this case, the surroundings will actually get colder. All right, here's our example of that. So here's that same reaction. So what happens is these two chemicals, carbon dioxide and water, absorb in a plant, will absorb solar energy. That energy will go into these two guys and make glucose and oxygen, which now have a bigger energy than these two guys that we started out with by this amount. Okay. So the energy difference between these two guys is how much energy the sun has put into it. So in this case, so in terms of exothermic reaction, the reactant has more initial energy than the product. In terms of endothermic reaction, it's the opposite. The product has more internal energy than the reactant. Okay. All right, so we can see that here. So the change, so I start out with these two guys down here. I have to add heat or solar energy, and they make these guys here. So this is a graph. This is internal energy. Higher is higher internal energy, lower is lower internal energy. So this photosynthesis starts out with low energy substance, and it creates a high energy substance. Okay, so now chemistry has its own terms for things, and I've been using the word internal energy. Every substance has internal energy. In chemistry, we don't call that internal energy, we call that enthalpy, and we give it the letter H. So what we want to do when we look at a chemical reaction is what is the difference between the enthalpy of a reactant and the enthalpy of the product. And the way to do that is to measure how much heat or energy is given off or absorbed, and then we can figure out the difference between the two enthalpies. Okay, in the previous case with photosynthesis, we replaced internal energy with enthalpy. So this guy has a lower, so our reactant has a lower enthalpy, and you have to add heat to create a higher enthalpy, and so the product has more energy than the reactant. If you notice here, the arrow goes up. In an exothermic reaction, the arrow would be going down, the reactant would be at the top, and the product would be at the bottom. For endols, it's the opposite, reactant at the bottom, product at the top. Okay, now let's look at a confined situation. Suppose I take some propane and oxygen and I put it in a special container. Now what makes this container special is when the reaction takes place, the products, oxygen and carbon dioxide, will stay in the container. However, any heat that is made will move out of the container to heat the outside. Whatever the outside is, it will heat it up. Now, there are different kinds of containers, and they have scientific names. One's called a closed system, and that's what we're doing. And that's where matter is contained in the container, but energy can move in and out of it. There's another kind of container called open systems, where it lets both matter and energy in and out. We are open systems. We take in energy, we eat food, we let it's matter, and the matter comes out of us. And that's energy, and energy goes in and out of us. So matter, we are open systems. Isolated systems is where the container doesn't let anything out. We are going to use a closed system, okay, for this scenario. So what we are interested in is the difference of enthalpy, the internal energy, of the reactant and the enthalpy of the product. We want to figure out the actual value of the reactant, the propane and oxygen, and the difference between its enthalpy and the enthalpy of the carbon dioxide and water. So we want to figure out the difference in the enthalpies. All right. Right. The way to do that is to find out how much does the heat that's given off, and that heat is the same as the energy that is different. So how are we going to measure heat? So we're going to do this experiment. We're going to put it in a container, or let it go going, and then it's going to release heat. So how are we going to measure that heat? Okay, what is heat? I mean, so we know that heat is molecules moving around, but how are we going to measure it? Well, unfortunately, there's no heat meter. You just can't put it on a scale and measure it. Okay, but we can figure out the heat doing it sort of sideways. We know when we heat something, it raises temperature, or if you go down, it lowers temperature. So what is temperature? Well, temperature isn't heat. Okay, and there's many definitions, but for our sake, I'm going to use this definition. Temperature measures the amount of heat in a substance per mass. So you can say it's how much heat there is in the mass in a substance per mass. It's kind of like density. Density is the mass per volume, how much mass is in volume. This is how much heat is in a mass. So I often call temperature heat density. And notice it's not heat. So one way to think about it is this. Suppose you have a certain amount of heat, 1,000 calories, and we put it in a pound of water. And then we take another 1,000 calories of heat and we put it in 5 pounds of water. Which one of these two will have the higher heat density? Okay, the 1 pound has 1,000 per pound. Okay, the 5 pounds have 1,000 calories per 5 pounds, or 200 calories per pound. So you can see that the 1,000 calories per pound has a higher heat density, and therefore it's going to have a higher temperature. So we can say that temperature of a substance is related to its mass, but it's kind of in an inverse or opposite matter. A bigger mass will, with the same amount of heat added to a smaller mass, will have a lower temperature. Think about it. If you heat up a cup of water and a gallon of water with the same amount of heat, to get it to the same temperature, the gallon of water is going to take a lot more. I mean, if you want to heat both of them up to the same temperature, it's going to take more heat to get the gallon of water to that temperature. So what we can say is the temperature is related to the opposite of the mass. And this is a squiggly, which is kind of related. It's called a relation term. So the temperature is related to the opposite of the mass. And in math, opposite is the inverse. So you can say temperature is related to the inverse of the mass, or you could write it like this. It doesn't say equal, it just says related. Right. The temperature is also related to how much heat you add. If you add 200 calories to a cup of water and 100 calories to a cup of water, the cup with 200 calories will have a higher temperature. So this is a direct relationship. So if the temperature is directly related to the heat, okay, we can write it symbolically as T squiggly Q. Q is a symbol for heat. Okay, another component of temperature of an object is the object itself. For example, often when we do labs, we have to heat up some substance like water, and to do this we set up the following. So I have a Bunsen burner here, I have a ring stand, okay, and I put a beaker and I put water in it, and then what I do is I light it, okay, and then what I'm going to do, little added thing, I'm going to put a thermometer in the water, and then I'm also going to attach a thermometer to this ring, and I don't want it sticking directly in the heat. I'll have it over here, okay, so I'll have a thermometer over here, right. So I let the Bunsen burner, let it heat up, raising the temperature of the water. However, we are not only heating up the water, we're heating everything else up. Well, the Bunsen burner is giving out the same amount of heat to everything. I put the thermometer in the water and strap it to the ring. Okay, and let's say the mass of the water and the ring weigh the same. And then I take a look at the two thermometers after like a minute. What will I notice? You will notice that the ring's temperature has gone up way higher than the water, okay? So there's something about the ring that can change temperature way easier than water. And that's the quality of the substance. So what's going on? It turns out that water can take the heat and not change its temperature very much, while the ring changes more. Okay, so the water is calm and cool and collected. It can take a lot of heat and not change, while the ring will change very quickly. What you can say is water has temperature inertia, and there's that word inertia. Remember, inertia means inability to move. So water has the inability to change its temperature. It's just a quality that it has. It's harder to change its temperature, while the metal has a smaller temperature inertia. Well, every substance has its own and specific temperature inertia. Some have higher temperature inertias like water. It's hard to change their temperature. And others will have lower temperature inertias like metals. We don't use the word temperature inertia. That would just hopefully give you an idea. We use the term heat capacity instead. What this means is that a substance with a high heat capacity can store heat without changing temperature. very easily, which is basically our temperature inertia. So a substance with high heat capacity will have a lower temperature when a given amount of heat is added. So again, it's kind of like mass. The more heat capacity, the less change in temperature. Okay, so what we do is we have an opposite effect. Temperature is related to the opposite of the heat capacity, or the inverse, 1 over the heat capacity. And we could write it as this. Okay, temperature is related to the opposite of the heat capacity. Heat capacity is given a letter C. So heat capacity is a really, really important thing. It helps explain a lot what has happened in the world over now and into the past. And I have a lecture that I may be putting up that talks about heat capacity and how important it is. Just for fun. So now what we can do is we have three things. We can tie them all together. We have mass, heat, and heat capacity. And actually we can come up with an inequality. So the temperature of a substance is related to the heat you add to it, okay, divided by the mass of the substance and the heat capacity. So we can write out the equation like this. So the temperature is directly related to the heat and inversely related to the mass and the heat capacity. Okay, often we don't really care about the temperature. We're interested in how temperature change, and so we write the equation like this. Delta T equals Q divided by MC, and delta means change. So change in temperature is equal to the amount of heat added divided by the mass and the heat capacity. All right, let's go back to chemistry. See how this applies. We wanted to figure out how much heat our reaction gave off when it's combusting propane. And what we want to do is find out the difference between the enthalpy of our product, our reactant, and our product. And the way to do that is to measure the heat that is given off. That says heat. So once I figure out, I can figure out the differences in sizes of these two guys. Okay, the problem is that we can't measure this heat. But if we look at the equation I just put up, okay, what we can do is that we can do simple math. I hope you can do it. If you can't, well, that's okay, because I'll do it for you. You can rearrange this equation for heat. Okay, simple algebra, right, will give you this. So the heat is equal to the mass of the substance, mass of, we'll talk about that in a second, times the heat capacity times the change in temperature. So how can we figure out, so this, we're going to use this equation here to figure out this guy up here, which is the same number as the difference between these two guys here. So how am I going to do this? So let's go back to the container. Let's take the container and put it in a 1 liter of water. Okay, so you have this can that's all closed up that has propane and oxygen in it. Okay, and you drop it in a liter of water. A liter is 1,000 mils, and it's known that each mil of water weighs about 1 gram. So if I have 1,000 mils, that weighs about, or mass is 1,000 grams. We then somehow start the reaction, which I'm going to talk about at the end of this lecture, how that happens. As it takes place, as the heat is released and reaction gets going, the reactant turns into a product, gives off heat. The heat will move out of the container and moves into the water. Okay, so you can kind of think about it. Here's your container, okay, and it's in water. The reaction takes place, and the heat that's given off in this reaction goes out and heats up the water. And let's say it changed the temperature of the water by 10 degrees Celsius. Well, I can find out how much heat has been released in the water by using my equation right here. All right. So if I can figure, so I'm going to figure out how much heat, this right here, since this is the heat that's been delivered into the water. And that heat is going to be same as the heat in the enthalpy difference between these two guys. Okay, so I know the mass of the water, it's 1,000 grams. I know the heat capacity of water, I gave that to you before. And I know the temperature change is 10 degrees. Okay, do the math. So 1,000 grams times 1 calorie per gram per Celsius times 10 Celsius, and you end up with 10,000 calories is released in this reaction. So when the reactant goes to the product, it gives off 10,000 calories. Okay, and that turns out that amount is the difference in these two guys' enthalpies. Okay, now I'm not gonna. You don't have to worry about it. Just know that if you're using this, all the units are the same, grams, calories, and Celsius. You don't have to worry about the units as long as you set the equation up right. So it's mass 1,000 times 1 times 10. So 1,000 times 10 is 10,000. And the units for heat are always going to be calories when we do this for now. Okay, so this is what we have. We have our reactant and then our product, and the difference between the two are 10,000 calories. So I know that this guy right here, my reactant, has 10,000 more calories in it than my product. Okay, this is exothermic reaction. The reactant has more enthalpy than product. Okay, so this guy has 10,000 more than this guy down here. Okay, so this number here is 10,000, which is the difference between these two guys. Okay, now I need to clarify. Suppose I have 1 pound of propane and it produces 10,000 calories, like the example. When it's combusted, you probably can guess. When it's combusted. And you could probably guess if I have 2 pounds, how many calories it would produce. It would be 20,000. So the amount of heat that is produced is related to the amount of substance we use. Not all combustion reactions will give off 10,000 calories. So when I write this chemical reaction, I have to know how much of the substance I started out with. So what you would do is you'd take your 10,000 calories and you would divide it by how much of your reactant you have. So this case, if I started with 1 pound, it would have been 10,000 calories per 1 pound. Now, if the reaction when I did it in the canister was 2 pounds, then it would have been 10,000 calories per 2 pounds. So that's a really important point, and to standardize our chemical reactions and our enthalpies. Okay, endothermic reactions. In this case, we have our container, we have our water, and what happens in these cases is it's that to turn the reactant into product, you need to add heat. And where does the heat come from? It comes from the water. So what's going to happen is the heat's going to go into the water, and it's going to into the container, and it's going to cause this reaction to take place. So in this case, the reactant's going to have smaller enthalpy than the product by this amount. Okay, so let's say the heat, in this case, temperature, the water temperature will go down because it's losing heat, and the heat will go in to convert the reactant to product, and then you can measure. So what you do is you just measure the temperature. When it goes down, you put it in the same equation, but instead of putting it on the right side of the equation, like in the exothermic reactions, you put it on the left side of the equation. That means heat has gone in reaction. It also tells me that the reactant has a lower enthalpy than the product. which is the opposite of the exo, which was the other way around. Okay, now the final thing to do with energy is something we just kind of scan over, but chemical reactions. If I take a propane tank and I open the valve, what's going to happen is that propane gas is going to come in contact with air. Well, the air has oxygen, so technically I have everything I need to get that reaction going. I have propane and oxygen, but it doesn't go. Okay, they just bounce around each other and don't even notice each other. Okay, so but the chemical reaction says when you take propane and oxygen, they make carbon dioxide and water. Well, that's not the case. Okay, there's something missing. And what is that missing? Well, it turns out that every single chemical reaction sort of has a reaction inertia. Again, there's that word inertia. Inertia means ability to happen. So every chemical reaction has an inability to get going, to take place. Every single. Some chemical reactions have a higher reaction inertia. Some have a lower. Okay. Now, again, we don't call it reaction inertia. It's this way kind of to think about it. It's called the activation energy, or energy of activation. So how much energy does it take to get this chemical reaction going? To get it off its butt and get it going. And here's two examples, okay? So here's your starting, okay? And what you have to do is you have to lift it up a little bit, and then once you get it up to here, it comes flying down, all right? Okay, then you have this reaction, starts out here, but you have to lift it up a lot to get it going, all right? Okay, so what we're interested in now is how do we get it going? What are the tricks to get it pushed over this hill and get it going? So how can a reaction overcome this inertia? How can it get its energy of activation? Well, you may have heard people say they'll put a fire to your rear and that will get you going. Well, the same applies to chemical reactions and having them overcome their inertia. Every single chemical reaction needs a kick in the butt to get going. Some need it a lot. For instance, combustion of propane actually requires a good kick in the butt. You need to light a match, okay? While other chemical reactions don't hardly need anything. For instance, if you have some nitroglycerin, okay, which can explode, you just have to drop it on the floor and it'll go boom. In fact, most explosives have a low activation energy. Okay, finally, how is this all going to apply? Okay, hopefully there may be a quiz on this, but the main thing you'll do, there'll be a short quiz, going over this, just like the rest of the quizzes. And actually, it's part of the lab, so this won't be, this will be part of a lab. So there'll be two parts of this lab. One is doing a quiz on this PowerPoint. And the other one is going to be you'll be watching me do a lab, and then you'll be writing down the data for that, and then what you'll be doing is you'll be coming up with some values. And I have the lab posted, and it's called Finding the Heat of Fusion Water. And what you're doing is you're finding how much heat is needed to melt a certain amount of ice. So it's called the heat. So what you're going to do is add the heat of fusion, that's its technical name, plus ice to give me water. Now, why do we use the word fusion? Because melting is the opposite of freezing. When you freeze something, you're fusing things together. So when you freeze, you fuse water molecules together in a sense. And then when you melt them, you unfreeze them or unfuse them. So if you know the unfusion heat, the amount of heat to unfuse something, it's also the energy to fuse. So even though we call it heat of fusion, it could be also called the heat of unfusion. So what you're going to do is figure this value out. And you can see this is an endothermic reaction. That means that the product water will have more enthalpy in it than the ice started. And what you want to do is find out the difference. Okay, and so what you're going to do is you're going to put some ice in the water. You're going to take some ice. You're going to put it into water, put it at a thermometer, and just because the water's got heat, and that heat's going to go into the ice, and it's going to start to melt the ice. Eventually, all the ice is going to melt, and then you're going to take the final temperature it took, the beginning and final temperatures to melt all that ice. Okay, so you'll have the temperature change. Okay, you know the mass of the water, so that's one of the steps you do is you weigh the mass of water without the ice, and you know the heat capacity. Okay, so what you do then is you just do our formula: Q equals MC delta C delta T. C is the heat capacity of water, and then just multiply those three numbers together. And that'll tell you how much heat was required to melt the ice into the water. Now, what you want to do, just like we did in the previous slide about clarifying, is that you want to make sure you know how much heat is per mass of ice. So you're going to have to measure the mass of the ice as well. All right. Now, there's a procedure on how to do that. And then what you're going to do is take this value that you got here, the heat of fusion, then divide it by the mass of the ice. Okay, and that'll give our answer, which will be the heat of fusion per gram of ice. Okay, so that's it, and later.